The design of the slab follows the procedure in RC design. However, there are numerous checks according to the limit states. Welcome to Bridge Engineering. The problem involves a bridge of 18-meter length. The 200 mm thick deck is supported by AASHTO Type 2 I girders, spaced evenly at 2.4 meters on centers. The concrete deck strength is 28 megapascal, with steel yield strength of 415. Prior computations show the factored moment is 65 kilonewton-meter per meter, and factored shear is 90 kilonewtons for strength 1 limit state, and the service moment is 40 kilonewton-meter per meter under service 1. The bridge is located in standard exposure or class 1. The design of reinforcement will have to be checked with the different limit states. To summarize the given, the deck thickness is 200 millimeters and girder spacing is 2400 millimeters. F'C is 28 megapascal with Fy of 415. Using strip method, the design strip width is standardized at 1000 millimeters. The length of the bridge is 18 meters, and Type 2 I girders are used. The moment for strength is 65 kilonewton-meter per meter, while shear is 90 kilonewtons. There is also a moment for service limit state of 40 kilonewton-meter per meter. We start the design with the main reinforcement, which is found at the bottom, along the width of the bridge. We are to look for the required steel area using the comparison of the ultimate moment from the loads to the nominal moment, taken from phi AS/Fy with D minus A over 2. Before we can solve AS, we still need the block area A, from AS/Fy upon 0.85 of F'C times B, where we needed AS again. From the equation, we look for D, or the effective depth, by taking the deck thickness less the concrete cover and half the bar diameter. From the AASHTO table, we use a cover of 25 millimeters as we are solving the bottom reinforcement. So using D16 bar, D is then solved as 200 less 25 minus half of 16, giving 167 mm. Now let's get back to the two equations, where AS are unknown. We can still solve for the steel area by iteration. That's by assuming a value for A and verifying it through iterations. Or we can coin the two equations by substituting A into M sub U equation, which gives the longer one. We use this quadratic formula and plug 28 for F'C, 1000 for B, and 167 for the depth. Fy is 415, and the given ultimate moment is taken from the strength limit state, which is 65 kilonewton-meter per meter. AS is simplified as 1106 square millimeter per meter. Now that we have the steel area, we take the number of bars by dividing this area by the cross-sectional area of D16, giving 5.72 pieces. Take the spacing from this number, making 1000 over 5.72, where we get 174.83, rounded to 175 mm. We might have rounded the value up, but we are still safe as the number of bars wasn't rounded. There are also bars for the top reinforcement. This is using the negative moment, but it would still be safe to use the positive moment as normally this is higher. Using D16, we look for the cover from the table. This time, the location is top, where the cover is 50 mm. D is 10, 200 less 50 minus half the bar diameter, turning out as 142 mm. Solve for AS with F prime C of 28, B of 1000, D is 142, Fy is 415, and M sub U is 65. The required steel area is 1,335 square millimeters per meter. With diameter 16 rebars, 1,335 divided by its cross-sectional area gives 6.64 pieces. Then the spacing is computed as 1,000 over 6.64, giving 150.6 mm. At this point, we round it to 150, as that would be easier to lay out on site. After finishing the top and bottom transverse reinforcement, we then compute for the longitudinal bars, which will take care of temperature and shrinkage. AASHTO provides an equation for the steel area for shrinkage and temperature, given as 3/4 of the gross area divided by the steel's yield strength. The concrete's gross area is taken per strip, making 1,000 by 200, and the steel grade is 415. So the area is 361 square millimeters per meter. When using 12 mm RSB, we take 3.19 bars per strip, and the spacing is 1,000 over 3.19, or 313.48, rounded to 300 millimeters on centers. These bars are placed with the transverse bars on top and bottom of the deck. Now that we have identified the rebars for transverse and longitudinal directions, we verify the reinforcement using the limit states. We start with crack control. This involves the service limit state. The cracks can be countered by the spacing of bars, so we define the maximum spacing of bars when cracks can occur. The maximum spacing is 123,000 of gamma E over beta S with F of double S, then deduct twice of D sub C. With new parameters to solve, we look for FSS first. This is through the moment solved using service limit factors over the product of AS, J, and D. The moment is provided as 40 kN per meter. Let's check the bottom bars. The steel area was solved as 1,106 square mm, and D was also identified as 167 millimeters. What we have to look for is J, or the lever arm coefficient. J requires the location of the neutral axis K, and K is the root of 2 times rho times n plus the square of the product of rho and n, then subtract rho by n. So there are 2 more parameters for us to solve. For the reinforcement ratio, rho is the area over B times D. We earlier found the steel area as 1,106, then divide the quantity of 1,000 and 167, turning out as 0.00662. For the modular ratio N, we take the moduli of the elasticity for steel and concrete. Steel has 200,000 megapascal, while we can solve for E sub C as 4,700 times the root of F prime C, or 4,700 with the root of 28, giving 24,870 megapascal. The modular ratio is then 200,000 over 24,870, which is simplified as 8.04, taken as 8. Then we can compute for K by placing rho of 0.00662 and N of 8, and K turned out to be 0.28. After knowing K, we then can solve for the lever arm factor, as J is equal to 1 minus a third of K. Plugging in K of 0.28, we get J as 0.906. With all parameters figured out, we can solve for F sub SS, which is the moment factored in service divided by 1106 by 0.906 multiplied by 167. FSS is 239.034 megapascal. In case we use the arbitrary constant J equal to 0.88, FSS turns to be 246.1 megapascal. The next parameter to compute is beta sub S, which requires H and D sub C. H is the deck thickness of 200 millimeters. DC can be computed on both the top and bottom bars. DC is considered as the cover plus half the bar diameter. And for bottom bars, we take the cover of 25 mm plus half of 16, turning out as 33 millimeters. Beta S is then 1 plus 33 over 0.7 of 200 less 33, and that gives 1.28. With gamma E as 1, we can solve for the maximum spacing as 123,000 times 1 over 1.28 over 239.034 minus twice of 33. And this shows 336.01 millimeters. How do we interpret this? The computed spacing earlier is 150 mm. This is within the maximum of 336.01, so the bottom bar spacing is safe. Now for the top bars. We assume similar stresses at the top, which gives FSS of 239.034 megapascal. The steel area at the top is 1,335 square millimeters, and D is 142. However, beta S required D sub C, which is computed as the cover plus the radius of the bar, where the cover from the top is 50 mm, then add half of 16 millimeters to come up with 58 millimeters. Beta S is then 1 plus 58 upon 0.7 of the difference of 258, which results to 1.58. Use this in the maximum spacing equation and have 123,000 times 1 upon 1.58 of FSS, which was adopted from earlier, then subtract twice of 58, giving 209.68 millimeters. Again, this spacing is compared to the actual rebar spacing we designed as 150 mm, and it shows that our design is within the range. Hence, the top bar spacing is also safe. The last check is for shear. According to AASHTO, the nominal shear capacity is equal to the concrete strength, where 0.166 of the root of F prime C multiplied by the width and the depth is provided. We already know F prime C as 28 megapascal, B is 1000 mm, and D is 167. This is simplified as 146.7 kilonewtons. This is the strength of the design geometry. Now we factor it to have the nominal shear strength by multiplying it with phi, which is equal to 0.9, resulting to 132 kilonewtons. This is the one compared to the shear, resulting to the load, and in the problem, it was given as 90 kilonewtons. The nominal shear is greater, so the slab thickness is safe.